So here is the formula. Oh, let me ask, did any of you watch the video I said you should all watch?
Yeah.
Awesome, cool. So hopefully that helped you understand kind of where the formula actually comes from and how it's derived. I don't think we should really spend time doing that in class because it's I mean, it's not hard to derive, but it's kind of just a pain. So for all those of you online, if you haven't already, I certainly recommend watching the video that I posted in Canvas. It is well worth the 22 minutes to watch it, I think. Or 11 minutes if you watch it on double speed, right? I mean, you watch it faster. So I'll remind you of the formula for Taylor polynomials. We have that some function f of x, we can write it as f of a plus f prime of a times x minus a to the first plus f double prime of a times x minus a squared over 2 factorial. People usually write it so that just the derivative part is being divided by the n factorial. So technically there's a 1 factorial divided by there. Technically there's a 0 factorial divided by there, and so on. F triple prime of a over 3 factorial times x minus a cubed. And this is equal to the sum n equals 0 to infinity of the nth derivative of f evaluated at the center a over n factorial times x minus the center to the nth power. This is the Taylor polynomial for the function f of x centered, I can spell centered, at x equal to a. And sometimes this is the process we will actually use for finding the Taylor polynomial of a particular function. Let's look at an example. Let's say we want to find the Taylor polynomial for f of x equal to the natural log of x centered at, well, certainly not 0 because natural log of 0 is undefined. So we should pick a different point to center it at. We're usually centered at 1. So here's the process, or at least here's my process. You start taking some derivatives. So my function is natural log of x. The first derivative is 1 over x, which since I know I'm going to be taking a few more derivatives, I'm going to prefer to write as x to the negative 1. Then my second derivative is going to be negative x to the negative 2. My third derivative is going to be 2 times x to the negative third. My fourth derivative here is going to be, so let me actually start plugging in some values before I find the fourth derivative. So if I do f of 1 is 0, f prime of 1 is 1, f double prime of 1 is negative 1, f triple prime of 1 is 2. So here you might do this the following way. You might think, right, this is negative 6 times x to the negative fourth. If you plug in 1, I should be writing 4 there. You're going to get negative 6. But it might be more useful to think of this as negative 3 times 2. Because then when I do the next one, when I do the fifth derivative, instead of saying it's 24, I might say it's 4 times 3 times 2 times x to the negative fifth. And the fifth derivative of f evaluated at 1 is going to be how much? 4 times 3 times 2. Was that? Right. Which you could say is 24, but it might be more useful to say that that's 4 factorial. Because the next one, the sixth derivative, I'm just going to multiply that by negative 5. And you get negative 5 times 4 times 3 times 2 times x to the negative 6. And my sixth derivative is going to be negative 5 factorial. So it looks like I've found a pattern for the nth derivative evaluated at 1. It looks like my In fact, if I go down here, right, my nth derivative of x just looks like it's going to be -1 to the, well, I don't know, some kind of power here. Let's see, if it's the sixth one was negative, the fifth one was positive. So it looks like if n is odd, I need to be positive, like an n plus 1. And then we have, it looks like an n minus 1 factorial. So if I plug in 1, sorry, I forgot the x to the negative n plus 1, the negative n, sorry. That's how, now I probably shouldn't have even written this, because normally we don't care what the nth derivative of x is. We care what the nth derivative when you plug in 1 is. And I can see that when I plug in 1, it looks like my nth derivative at 1 is going to be, well, if it's the sixth derivative was 5 factorial, fifth derivative 4 factorial, fourth derivative 3 factorial. So it looks like it's going to be n minus 1 factorial. But then I also need to alternate the signs. So is -1 to the n going to work? It might. Let's see, if I plug in n equals 6, it should come out to be negative. But -1 to the 6th is positive. So I need to adjust by adding a 1 there. That'll get the signs right. So we're almost there. So here's the problem. Sometimes this doesn't work all the way back to, say, n equals 0, n equals 1, n equals 2, n equals 3. So let's see, if we plug in 0, it definitely doesn't work because -1 factorial is not defined. But you're also going to get 0 there, so it might not be a problem. Let's see, if I plug in n equals 1, 1 minus 1 is 0 factorial, and 0 factorial is 1. Important to know, 0 factorial is equal to 1. And then -1 to the 1 plus 1 is -1 squared, that gives me a 1. Check. If I plug in n equals 2, 2 minus 1 is 1, factorial is 1. And then -1 to the 2 plus 1 is -1 cubed, that's -1. So yeah, it looks like they're working out. So I could say that the natural log of x is equal to, all right, so here it's going to be, sorry, brain. I'm just going to write the terms first of all. So it's going to be, sorry, I'm having a problem, but I remember what, it's going to be f of 1 plus f prime of 1 over 1 factorial times x minus 1 to the first plus f double prime of 1 over 2 factorial x minus 1 squared, f triple prime of 1, 3 factorial, x minus 1 cubed, and so on. But check this out. Let's see what we get. I'm going to get f prime of 1 is 1 over 1 factorial times x minus 1. F double prime of 1 is -1 over 2 factorial times x minus 1 squared. F triple prime of 1 is 2 factorial over 3 factorial times x minus 1 cubed. Plus, if I keep going like this, it looks like every numerator is just the 1 less factorial over the denominator. So this 2 factorial over 3 factorial is just going to become 1/3. This next term here, which I didn't have room to write, is 3 factorial over 4 factorial. I forgot the minus sign, sorry. Times x minus 1 to the 4th. That's just going to be 1/4. Or if I want, I can kind of just look at the pattern and say, well, if I'm doing the sum from n equals somewhere to infinity of my f n of 1 over n factorial x minus 1 to the n. Well, that ends up being sum from n equals, we'll talk about the starting place in a minute here. Fn of 1 we just found was n minus 1 factorial times -1 to the n plus 1 times over n factorial times x minus 1 to the n. Okay, what's that -1 factorial over n factorial? Not quite. So let's see. I want to write down here. So n minus 1 factorial over n factorial. It is 1 over n. Because n factorial is n times n minus 1 times n minus 2 all the way down. And n minus 1 factorial is n minus 1 times n minus 2 times all the way down. And so the n minus 1's cancel, the n minus 2's cancel, and everything else cancels, leaving just a 1 over n. This really simplifies to just be the sum of 1 over n times negative 1 to the n plus 1 times x minus 1 to the n. And we are starting at n equal to 1, not 0. Because if n were 0, we would be dividing by 0. It's actually kind of funky. And you can write out terms, right? The terms would literally be x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on and so on and so on. There's the Taylor polynomial for the natural log of x. Sorry, x at a equals 1. There's another way to find this, but I don't think it's something we talk about in this class. So I'll let you all should let me know. I don't think it's going to come up, but if your teacher starts talking about taking derivatives or antiderivatives of Taylor polynomials or functions to get Taylor polynomials, let me know. I don't think that's covered in this class, but no, it's not the interval test. Right. It's this whole thing where like you say, like you can say, I'm going to find, like, for example, not that you really need to know this, I'm going to keep it brief. But if I wanted to say find for f of x equal to the arc tangent of x centered at x equal to 0, a equal to 0, sorry. You might recognize that finding a bunch of derivatives like this are really kind of gross, right? The first derivative is 1 over 1 plus, oh, did we cover the derivative arc tangent in this class? No, scratch that, garbage, sorry. All right, I don't need an example of this thing because we're not going to cover it. So I should just move on, even though I really like it. So let's look at a few more examples because we're going to move towards the thing which is really more useful. But let's say we want to find the Taylor polynomial for, did we already do e to the x? Okay, let's do it for e to the x. For e to the x, centered at x equals 0, a equals 0. E to the x is kind of the nicest one. Ooh, I just thought something cool. Huh, interesting. E to the x is really nice because when you do this, you're just going to, well, let's start taking derivatives. My first derivative, my function is e to the x. My first derivative is e to the x. My second derivative is still e to the x. So I can see that any derivative is going to be e to the x. And if I plug in my center, any derivative evaluated at 0 is going to be e to the 0, which is 1. So my Taylor polynomial is looking like, well, again, I like writing out the formula because I don't know. You can do it one of two ways. I kind of like writing out terms like f of 0 plus f prime of 0 times x to the first plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. It's equal to the sum from n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the n. And here, each of the things that's f of 0, f prime of 0, f double prime of 0, all those are just going to be 1. So here, we get the e to the x is equal to 1 plus x plus 1 over 2 factorial times x squared over x squared over 2 factorial plus x cubed over 3 factorial, and so on. That's the sum from n equals 0 to infinity of x to the n divided by n factorial. And you should definitely memorize this one. 100%. You should memorize this one. If there was ever a Taylor series centered at 0 to memorize, this would be the one. There are others you should also memorize, but this is top of the list. So let's answer another question by looking at something terrible. So what if we then said, okay, well, great, we did that, no big deal. And now I'm going to say, well, now let's make it a little spicier. Let's find the Taylor polynomial for f of x equal to e to the x squared. This is where things get terrible. And also not at all. But if you do this the wrong way, it will be terrible. So let's start. I'm going to start doing it the wrong way. You don't need to write this down if you don't want to, because we're not going to use it. So if I start, so this my function is e to the x squared. And f of 0 is 1. And f prime of x, I have to use the chain rule. It's e to the x squared times 2x. And f prime of 0 is going to be 0. The second derivative is going to be, we got to use the product rule. So it's the derivative e to the x squared. So e to the x squared times 2x plus e to the x squared times 2. If I plug, that's f double prime of x. If I plug in 0, f double prime of 0 is going to be 0 plus 2. And then the third derivative, oh boy, yeesh, that's going to suck, right? And it's going to just suck more and more and more and more the more we do this. And it's really, really hard this way to see what the pattern is for your nth derivative of x or your nth derivative of 0. Fortunately, there's an easier way. So here's what we already know. We know that e to the x, well, it's even right there. I'm just going to, so we know that our function from above f of x is e to the x, and that's 1 plus x squared over 2 factorial, and so on and so on. But now I'm essentially going to say, instead of finding f of x, this f of x, sorry, and I should have used a different name. I apologize, I didn't. Now we're going to find f of x squared, which is going to be e to the stuff, e to the x squared. And each of these x's here, I can just replace with x squared. So this is going to equal 1 plus stuff squared over 2 factorial plus stuff cubed over 3 factorial, and so on and so on and so on. And now the stuff, instead of being x like it was here, is x squared. And it even works in the final formula. Here the formula, like the summation formula, is the sum from n equals 0 to infinity of x to the n over n factorial. And here I'm just going to replace that x with, you guessed it, x squared. So e to the x squared can easily be written as the sum from n equals 0 to infinity of x to the 2n over n factorial. Kind of cool. Yeah. Well, that's why it's really important to memorize a few other very common Taylor polynomials, because the idea is if someone asks you to find the Taylor polynomial for like sine of x cubed, those derivatives get really gross really fast. But if you know the Taylor polynomial for sine of x, which is a well-known Taylor polynomial, which we're going to do in just a second here, it's really easy to just then substitute in x cubed. So that's kind of the idea, is there's a few that we really like. Sometimes you just have to derive one, and it's terrible. But most of the time, when we're being asked, to do this, we're falling back on a set of like 3 or 4 or 5 well-known Taylor polynomials and kind of manipulating them. So let's actually talk about sine of x. And we're going to do sine of x centered at 0. And I'm not going to show it since I already said it like last week, but I will just remind everybody that for this polynomial here, the interval of convergence is everything. The radius of convergence is infinity. So this converges for all x. You could certainly show it by applying the ratio test. We'll show it for sine next, in case you forgot. Okay, so For sine of x, x equals 0. All right, so I got to find some derivatives here. So my first derivative is going to be cosine of x. My second derivative is going to be negative sine of x. My third derivative is going to be negative cosine of x. My fourth derivative is going to be negative sine of x, which is just sine of x. And I'm back to where I started. So then I know that cosine of x is also my fifth derivative. It's also my ninth derivative. Any other multiple of 4 plus 1. And negative sine of x, in addition to being my second derivative, is also my sixth derivative. It's also my 10th derivative. And so on here, right? This would be the 7th and the 11th. This would be what? Yeah. No, the only, sorry, I should, by same concept, you mean this cycle of repeating derivatives? Yeah, no, it's only for sine and cosine. Tangent, the first derivative tangent is secant squared. And the derivative secant squared, we have to use the chain rule. We get 2 times secant tangent. And it just gets grosser and grosser. So here what we can say is, I know that f prime of 0, well, cosine of 0 is 1. And f double prime of 0, sine of 0 is 0. F triple prime of 0 is negative cosine of 0, which is negative 1. And the fourth derivative is going to be 0 again. And the fifth derivative is back to being 1. And the sixth derivative is 0. So we've got this pattern when your function is sine, where the derivatives are going to be 1, 0, negative 1, 0. 1, 0, negative 1, 0. 1, 0, negative 1, 0. Forever and ever and ever. That's our pattern of our nth derivative. Yeah.
Is that for the cosine of x? Is that f to the 5?
Yeah, that is f. That is the fifth derivative of f at 0.
Oh, and then it goes down to 4. Like 4 is the one that decided us.
That's a 9. Sorry, yeah, that's a 9. I know. Sorry, I wrote kind of small there. Let me zoom in a little bit so you can see that a little bit better. And maybe better. Sorry, I wrote too small. Actually, I guess this really starts at 0, right? Because sine of 0 is 0. Okay, so so there's my f of 0, f prime of 0, f double prime of 0, et cetera, et cetera, et cetera. So now when I'm going to start writing out my pattern, here's what my pattern is going to look like. It's going to look like 0 plus 1 times x to the first plus 0 times x squared over 2 factorial plus negative 1 times x cubed over 3 factorial plus 0 times x to the fourth over 4 factorial plus 1 times x to the fifth over 5 factorial. And it just goes on and on like this. So notably, which terms, what kind of powers do we only end up with? Odd powers. We only get odd powers in the Taylor polynomial for sine. The sine of x is equal to x, and then they alternate, right? Every other term is good, every other non-zero term is going to be positive or negative. So it's minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on and so on and so on. And the way we write this formula typically in the summation formula is the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the. That gives you, right, 2n plus 1 gives you every odd number, and 2n plus 1 factorial also every same odd number, and then negative 1 to the n alternates, starting with positive and then going negative, positive, negative. Two things I want to say here. No, it's not. Oh, I know what I want to say. Well, actually, I'll say that in a minute here. So then, for example, if somebody said, okay, great, well, now use that to find, I don't know, tell me What's the Taylor polynomial? Centered at x equal to 0 for f of x equal to x squared times sine of x cubed. Well, you're going to take your sine one and replace x with x cubed. So just like sine of x is equal to all the odd powers, sine of x cubed is going to be x cubed minus x cubed cubed over 3 factorial plus x cubed to the 5th over 5 factorial minus x cubed to the 7th over 7 factorial. And that's going to be the sum from n equals 0 to infinity. Instead of having x to the 2n plus 1, it's going to be x cubed to the 2n plus 1 over 2n plus 1 factorial times -1 to the n. Questions?
So in most cases, we know like the general like common Taylor. Like, this is a different elevated form.
Right. This is just a different thing that we're doing. And then to multiply that by x squared, I'm literally just going to multiply every term by x squared. So x squared times sine of x cubed is going to be x squared times x to the 3rd minus x squared times x cubed over 3 factorial plus x squared times x cubed to the 5th, 5 factorial, and so on. And so I literally can just multiply the inside of this thing by x squared. So I'm really going to have is sum from n equals 0 to infinity of x squared times x cubed to the 2n plus 1, 2n plus 1 factorial, and -1 to the n. And what I would probably do is I probably would simplify this just a tiny bit. Because x cubed to the 2n plus 1, I can multiply those powers together. X cubed to the 2n plus 1 is x to the 3 times 2n plus 1, which is x to the 6n plus 3. And then I could multiply that by x squared to get x to the 6n plus 5. Sorry, you can't see that. What's that? You're multiplying each term by that thing, so you can just throw it into the summation. Yeah. So here I would write this as the sum from n equals 0 to infinity of x to the 6n plus 3. Sorry, 6n plus 5. Got the x squared there. Times -1 to the n all over 2n plus 1. Well, I know what I was going to say about this. I was going to talk about what the interval convergence for this was. So I'm going to go back to my previous page because I have some room on it. So cover this up. There it goes. We'll go back to work. So for a second, I just want to talk about real briefly here. What about the interval or the radius of convergence? I guess I could ask about. Well, if I look at this thing, I'm just gonna no. Let's be real. I'm not gonna squeeze that in there. Not gonna fit. I'm gonna be trying to cram in small writing. You'd be like, James, is that a 5 or a 9? You're like, obviously, can't you tell? Okay, so for sine of x equal to the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times -1 to the n. If I want to find the radius of convergence, I'm going to use the ratio test. So the limit n goes to infinity of the absolute value x to the 2 times n plus 1 plus 1. I'm replacing the n with n plus 1 over 2 times n plus 1 factorial. And then I guess I'll write -1 to the n plus 1, even though I don't really need it. And then times the reciprocal of that, or sorry, yeah, the reciprocal of that. So 2n plus 1 factorial over x to the 2n plus 1, and then -1 to the n. Okay, so here's what's going to happen. I should simplify first. Limit as n goes to infinity of the absolute value. I've got x to the 2n plus 2 plus 1 is 2n plus 3. And divided by x to the 2n plus 1. And then the negative 1 to the n plus 1. I don't even know why I'm writing it. Those are going to cancel out and give me a negative 1. The absolute value of negative 1 is just 1. And then finally, the 2n plus 1 factorial over 2 times n plus 1 is 2n plus 2, plus another one is 2n plus 3. Okay, here's what we get. Limit n goes to infinity. X to the 2n plus 3 over x to the 2n plus 1. Subtract the powers, you get x squared. And 2n plus 1 factorial over 2n plus 3 factorial. Well, 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n, all the rest. The rest of that is 2n plus 1 factorial. So the 2n plus 1 factorial will cancel with 2n plus 1 factorial, and you're left with 2n plus 3 times 2n plus 2 in the denominator. And then as n goes to infinity, you're going to have x squared divided by infinity. And x squared is a real number, so a real number divided by infinity is going to be 0. And this is always less than 1 for any x. So this converges. So I should say sine of x equal to the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n, converges for all values of x. So what this really means is that you could find sine of anything by taking the literal infinite sum of that. Kind of weird. It's actually really weird when you think about it, because, like, for example, we know that sine of pi over 6 is equal to 1/2. It's true, right? It's one of those known trig values. So, but you can also write out an infinite series. You can say, well, I'm also going to say it's equal to pi over 6 minus pi over 6. You don't need to write this down. Over 3 factorial plus pi over 6 to the 5th, 5 factorial, and so on and so on and so on. It's kind of crazy that this infinite sum of very irrational things would add up to 1/2. But it does. Okay. Cosine, we should also know. So here's the nice thing about cosine. It's virtually the same as sine. In fact, yeah, I kind of want to show you the way people usually do this. So you could find cosine the same way by finding like the first 4 derivatives and getting the pattern. And when you do it that way, you will see that you get all the even terms for cosine instead of all the odd terms. And they have the same pattern. But you can also do this. We know that sine of x is equal to x minus x squared, sorry, x cubed factorial plus x to the 5th. I know I've written this like 7 times. Minus. Just start off with a new piece of paper. Fine. Let's try one more time. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And the pattern continues. What's the derivative of sine? Right. So we take the derivative, we differentiate both sides, which is kind of the thing I was referring to earlier. There is this theorem that says you can differentiate both sides of this and you get inequality. And the thing that's the theorem is that the radius of convergence doesn't actually change. So derivative of sine is cosine. What's the derivative of x? What's the derivative of x cubed? So 3x squared over 3 factorial. I don't need to use the quotient rule here, right? Because it's just dividing by a constant. And then I'm going to get plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial, and so on and so on. But 3 over 3 factorial, well, 3 factorial is 3 times 2 times 1. The 3's cancel, and you're left with a 2 times 1, which is 2 factorial. This is really equal to 1 minus x squared over 2 factorial. And 5 factorial is really 5 times 4 times 3 times 2 times 1. The 5's cancel, you're left with x to the 4th over 4 factorial. And then here you're going to get x to the 6th over 6 factorial. Oops. So sine and cosine have virtually the same exact pattern. It's just that cosine has the even powers, sine has the odd. Well, I can't, so 3 over 3 factorial is 3 over 3 times 2 times 1.
Oh, okay.
What's 2 times 1? 2 factorial, but this is, you're right, it is also 2. And then similarly, 5 over 5 factorial is 5 over 5 times 4 times 3 times 2 times 1. The 5's cancel and you're left with 1 over right.
So what's the root between the sine and cosine?
Well, let me answer your question with a different observation here. Graphically, if I graph sine, and it's been a while, here's the graph of sine. And it's not okay, not my best work ever. Let me ask you all. Does sine have odd symmetry or even symmetry? I know it's been a while. So I'll remind you, a function is considered to be even if it has reflective symmetry across the y-axis. So if you could flip this around the y-axis and it looked the same, for example, like y equals x squared, that is an even function because it looks the same when you flip it around across the y-axis. This is not an even function, but it is an odd function. It has what's called rotational symmetry. If you rotate this 180 degrees around the origin, it looks the same as it did before. So sine is an odd function, and not at all surprisingly, not coincidentally, sine of x has all the odd powers of x. And in a similar way, cosine of x, which certainly is an even function, it has even symmetry. If you flip it across the y-axis, sorry, it looks the same as it did before. And cosine is all of the even powers of x, including, don't forget, including the first term here, which has an x to the 0th. And 0 is an even number. Right? 0 is an even number. Because to be even, you just have to be divisible by 2. 0 by 2. Yeah. Right, it's right. Whenever you're writing a factorial, it is the highest number multiplied by every lesser positive integer down to 1. Although you don't have to write the 1 because multiplied by 1. So here's what I would encourage you to know so far. There are 3, well, actually 4, but 3 that I think are important. So there are 3 Taylor polynomials, and 2 of them together kind of look like the other one. So here's e to the x. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Every power of x over the same factorial. And then sine of x is just the odd terms. And cosine of x is just the even terms, except we have to alternate signs. So sine of x is just, oh, there's the odd term. Take that one, but change it to being negative. Take that one, leave it positive. The next one will be negative, and so on. And then cosine is just the even terms. It's, well, 1, right? 1 is an even, I know 1's an odd number, but this is an even power of x because it is x to the 0th power. So you basically need all the terms. So I get 1 and then alternate, so minus x squared over 2 factorial plus x to the 4th over 4 minus x to the 6th. And I always kind of like, there's a really cool formula where these actually give together and make the same thing. We might talk about it if we have time next time. But these together kind of make up e to the x if you make them all positive. So you kind of get 3 in 1. Right? If you know e to the x, you can pull out cosine and sine from it pretty easily, I think. First, you should definitely memorize these 3 Taylor polynomials, in my opinion. You could also do that. I just feel like, but I feel like you use these so much that, I mean, to me, this pattern feels easy to remember. If you know that the pattern for sine is x to an odd power over the same odd number factorial, we alternate, and then cosine, it's very easy to just be like, well, instead of saying the word odd, say the word even, and you've got the same thing, right? X is every even power of x divided by that same power of factorial. If you really wanted to make it easy to remember, you could say that technically this first term here is x to the first over 1 factorial. And technically this first term here, even though it feels dumb to write it, is x to the 0th over 0 factorial. And just as a reminder, in case you've forgotten, 0 factorial is equal to 1. So it's not a problem. We're not dividing by 0 there. We're totally safe. Okay. And then we should also, it's good to be able to write the sigma formulas. So this is the sum from n equals 0 to infinity of x to the n over x factorial. This is the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1, or 2n plus 1 factorial. And this one is the sum from n equals 0 to infinity of -1 to the n times x to the 2n, or 2n factorial. Those three, I think, are definitely worth memorizing. There are a couple others I also think are worth memorizing, but these are probably the most important of them. So then we could ask a question like, I want to ask that question. No. I could ask a question like, what are the first 4 non-zero terms of e to the x times sine of x? And you could do this either way. You could start taking, I mean, this wouldn't be so terrible. You could take 4 derivatives of this and probably get there. But it's going to be some product rule, right? Right. The first derivative is going to be e to the x times sine plus e to the x times cosine. And then the next derivative is going to be e to the x times sine plus e to the x times cosine plus e to the x times cosine plus e to the x times negative sine. It feels like I don't want to do that. Instead, here's what we should do. I know that e to the x times sine of x is going to be, well, e to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, plus x to the 4th over 4 factorial. And sine of x is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. And I might throw in more terms if I need them. And then we just start multiplying it out, multiplying the smallest power things by the smallest power things. So let's see. The smallest power I think I can get is just x to the first. So if I do a 1 times x, that'll give me an x. Okay. Can I get an x squared? Can I get an x squared? I don't think I can, because here I'm going to do, oh, I can. I thought I couldn't. I was thinking 1 times x cubed is easier, but x times x will give me an x squared. So there's my x squared. But I don't see any other x squared. So now, how about x cubed? Well, here's the thing that becomes challenging the further out you get. There is more than one way to get an x to the 3rd power. I could do 1 times negative x cubed over 3 factorial. But I could also do x squared over 2 factorial times x. That's going to be plus x squared over 2 factorial minus x times, oops. Sorry, I should have said x cubed. I apologize. X cubed over 2 factorial, x times x squared over 2 factorial times x, and then 1 times negative x cubed, so minus x cubed over 3 factorial. And if that was going to be 0, then I would have to keep going further, but it's not, because I can see those are different values. And then finally, for my x to the 4th term, I'm going to have, let's see, 1 won't multiply by anything over to give me x to the 4th. X times negative x cubed over 3 factorial, so I'm going to get a minus x to the 4th over 4 factorial. And that there. And then x squared won't multiply anything over here. That'll give me x to the 4th. But x cubed times x will give me a plus x to the 4th over 3 factorial. And then if I wanted to simplify this, I would write it as x plus x squared plus x cubed times, this is a 1/2 minus 1/6. And then here I have a plus x to the 4th times a 1/6 minus 1/24. If you really wanted to, you can simplify these fractions. 3/6 minus 1/6 is 2. 3/6 minus 1/6 is 2/6, which is 1/3. And 1/6 minus 1/24 is 4/24 minus 1/24, which is 3/24, which is 1/8. So the first 4 non-zero terms of this e to the x times sine of x would be x plus x squared plus 1/3 x cubed plus 1/8 x to the 4th. Kind of a pain, but it's a pretty typical type of question people like to ask. So what I would say the takeaway from today really is that you definitely want to know these and maybe a couple others we'll talk about next time, because someone's going to ask you, what's the standard polynomial for x to the 5th times cosine of x cubed? And it's going to be easy if you know what to do. You're going to say, great, throw in an x cubed for each of those x's, multiply the whole thing by x to the 5th. So I could do it super easily. If I just use this formula over here, it's going to be the sum from n equals 0 to infinity of -1 to the n times x to the 5th times, instead of x to the 2n, it's going to be x to the 3rd to the 2n, all over 2n factorial. And then simplify it if you want to, but I don't really want to. It's not terrible once you know the tricks. Yeah, Justin. So, okay, here's my explanation. And it's yeah, we can do it. So here's what I'll point out. You know that 5 to the 0 is 1, right? And the reason that's equal to 1 is really because of the additive law of exponents says it has to be, right? We have rules in math that once you make the rules, a whole bunch of other things follow as consequences, right? This is equal to 1 really because when you multiply 5 to the 0 times 5 squared, what do you do with those powers? Add them. So 0 plus 2 is, but 5 to the 0 times 25 equal to 25 means 5 to the 0 has to be 1. There's no other choice. Well, the same sort of thing is true when you talk about factorials. Okay, let me ask you all, have any of you taken a stats class or a probability class? So there's this idea of something called the choose function. And it's the number of, do any of you have to take a stats class at some point? Okay, great. You're definitely going to see this. So give me a minute. So there's this thing called the choose function, which is the number of ways you can choose so many things out of so many things. Let's say, yeah, fine. We'll take a minute here. Let's say we flip 3 coins. And they're different colors. So like you can have like a red coin, a blue coin, and a green coin. And like a green head and a blue tail, and a green tail is different than, sorry, a red head and a blue tail and a green tail is different than a blue head and a green and a red tail and a green tail. But so let's count the number of ways we can get things. So I can get 0 heads by getting all tails. I can get 1 head by getting either tails, tails, heads, tails, heads, tails, or heads, tails, tails. 2 heads, 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 tails, heads, tails, heads, tails, heads, heads. And finally, 3 heads, tails, tails, tails. I'm sorry. Tails, tails, tails. Heads, heads, heads. Here's the point. I'm gonna wrap it up here. So these numbers here, the number of ways you can get so many heads out of 3 coins, this number here is 3 choose 1. It is the number of ways you can get 1 head out of 3 flips. Either the first coin's a head, the second coin's a head, or the third coin's a head. Which makes sense, because if you have 3 things to pick from and you're only picking 1 of them, you can do that. But there's a formula for this, and the formula is 3 factorial over 1 factorial times the difference between them factorial. Okay, but what if I do 3 choose 0? How many ways are there of getting 0 heads out of 3 coin flips? Well, look, how many are there? There's 1. So when I do 3 choose 0, the formula for that is 3 factorial over 0 factorial times 3 minus 0 factorial, which ends up being 3 factorial over 0 factorial times 3 factorial. These cancel. But that better be one, so the formula works.